We have talked about bivariate Gaussian distribution. Now we will generalize it to more than two components. Here we have the multivariate Gaussian distribution. Okay, so this is a random vector of size n, and this random vector has a joint Gaussian distribution. Okay, and the joint PDF is given by this expression. Now here we have matrices and vectors. Be careful now. X here is a column vector, and this is the mean vector also. And this here, K, remember, is the covariance matrix. Okay, and in the denominator, we have 2 pi to the power n over 2, and the square root of the determinant of the covariance matrix. Okay, and n here is, of course, the dimension of this random vector x. And of course, if you actually look at the special case for n equals 2, you get this covariance matrix, and you can compute its determinant and its square root from this quite easily. And also you can invert this by, well, exchanging these two and then negating these two and then dividing by the determinant. You can easily get the inverse of this matrix. So if you write it, you will see that it's exactly the bivariate Gaussian distribution we have seen before. Okay, so this joint distribution tells us a very important thing. In general, and when we talked about bounding distributions or bounding probabilities, if you remember, I had said that if you just know the mean and the variance, it's the things you can do is very limited. You can just define some bounds, right? We have seen Markov inequality, Chebyshev inequality, and so on. If you don't have the distribution, just have moments, you can only bound the probabilities. But in fact, you see, the Gaussian distribution is entirely described by its mean and the covariance matrix, right? That means for any Gaussian distribution, it could be a single dimension, a random Gaussian random variable, or it could be a bivariate, or it could be a multivariate distribution. If you have the mean and the covariance matrix, you can characterize the distribution entirely, right? This is the beauty of Gaussian distribution. In the single random variable case, if you know the mean, if you know the variance, you have everything. You can just write the PDF, compute anything you like. And in the multivariate case, if you have the pairwise covariances, which will give you the covariance matrix, and if you have the mean vector, again, you know everything. You can derive anything you want. Now, there is a fine point here, a very important point. If x1, x2, etc., up to xn, let's say the components of this random vector, if we know that they are jointly Gaussian, any subset you take from these, okay, will also be jointly Gaussian. Now, you have to understand the term jointly Gaussian here, okay, because the converse is not true. What does that mean? If you know x1, x2, x3 up to xn is jointly Gaussian, then any subset x1, x2, x5, x3, x4, x7, any subset with any number of components will also be jointly Gaussian. But if I tell you that, okay, x1 is Gaussian, x2 is Gaussian, x3 is Gaussian, and if I ask you, are x1, x2, and x3 jointly Gaussian? The answer is no, not always, okay? For instance, if x1 and x2 are marginally Gaussian, this does not guarantee they will be jointly Gaussian, okay? Being jointly Gaussian is a very strong situation, okay? It's very useful, but it doesn't hold always, okay? So be careful about this. Let me give you an example here. Let's say we have 3 random variables, x, y, z, and we know that they are jointly Gaussian with this mean vector and covariance matrix, okay? And then you definitely know that x itself has mean 4, variance 4. It's Gaussian because it's a subset of these 3 random variables. Y by itself, it's a Gaussian with a mean of 1, variance of 8. Okay, sorry, this should be Z. And Z is also a Gaussian with a mean of 2 and variance of 12. And let's look at the pairs, X and Y together. X and Y together, again, will be jointly Gaussian. They will now be bivariate Gaussian. And the mean vector will be this. And this will be the covariance matrix. Okay. Similarly, X and Z, this will be the mean vector. This will be the covariance matrix. X and Z will be jointly Gaussian. Okay. Finally, if you look at Y and Z, sorry, I already did Y and Z. If you look at X and Z, these two will constitute the mean vector. And now this okay, sorry, this is not in. This will be your covariance matrix. Okay, so this is how you can also find the distribution of subsets of multivariate Gaussians. But if I tell you there is a fourth random variable, t, that's also Gaussian. If I give you its mean, if I give you its variance, I even give you the covariances between x and t, y and t, z and t. Even in this case, I cannot be sure this random vector x, y, z, t is jointly Gaussian, right? I don't know this. I know that x, y, z are jointly Gaussian. I also know that t is Gaussian, but together, I don't know how they behave. That is very important, okay? Jointly Gaussian implies marginally Gaussian, but marginally Gaussian may not mean jointly Gaussian. Be very careful about this.